Hello, everyone, and thank you for joining us this evening for the eighth week of the Rugby Research and Injury Prevention Group 2025 Analytics Series. Sophomore from the University of Michigan. Philip will be introducing us to SPSS. Philip, when you are ready, may you please share your screen?
Thank you very much, Indira. So as Indira said, we'll be kind of doing a brief introduction to SPSS today, which is statistical software used for data collection and analysis, sort of more specific to the social sciences as indicated by its name, the statistical package for the social science. Its main functions are to edit and analyze data through inputting data and uploading data, whether through corroborating files into SPSS or manually inputting data. It's very good for creating different columns, arrays, graphs, and different planes for that measure. And so the way that the files are sort of formatted in SPSS is through spreadsheets, through plain text files with like .txt or CSV, which, as you may know, are not necessarily spreadsheets, but they still kind of carry the data in ways that spreadsheets are. There's another form of how they can be stored. Relational databases, as we sort of talked about with the potential SQL database, as well as Stata and SAS. So those are two that are very similar as well. So sort of looking at the layout SPSS, depending on the version you have, it can be, a little bit older looking of a UI. However, it still sort of functions the same way. It looks very similar to Excel and Google Sheets in the layout. Um, Across the top, you have columns of variables and you have rows of numbers going down. You have the menu bar and you have the different icons or functions, as well as a startup menu in which you can put in commands and run your analyses. Using the data view, it's actually relatively similar to Excel in that you have your variables at the top, and through this, you can really create like arrays of either numbers, dates, binary variables, or continuous variables such as income. And this is displayed going down through the rows, allowing you to go and do analysis. So sort of looking at the variable view, this is known as like a meta view of all the data values, because all those variables are entered in the data sheet and they're sort of like viewable through that nature. Some can also be left blank, of course, either if there is a missing data value or that can be replaced with 999. This is typically called a code book in the sort of data storage world. So looking at the data analysis with SPSS, at the top, as you talked about with the menu bar, there is an analyze function in which you can include something such as descriptive statistics, and this can be used to demonstrate different like functions of the data that you're looking at, whether it is statistical analytical measures or more categorical measures. And then once you click through that, you sort of end up with another menu, as we talked about, in which you can sort of click on the functions that you want to display. So if we were looking at the income variable, which, as we saw in the previous slide, was a column including continuous variables of different income numbers, we could select that we want to see the mean as well as the minimum, maximum, and standard deviations to be displayed in, for example, a variable list. And then from there, we would run the code within SPSS, which would look like this as a descriptive statistic along with the column name. And then we would get the descriptive table looking in this fashion. So as we can see, it lists the minimum, maximum, and mean, as we talked about before with the menu that you were selecting, as well as the standard deviation, and even lists the amount of um, the number of cases in the variable of, for example, income. Looking at other forms of data analysis, as we've sort of talked about throughout all of the analytics series so far this year, there's a ton of different analytical measures you could use to analyze your data, including all of these, such as t-tests, chi-squared test, ANOVA, which Mina will be talking about today, as well as correlations and regressions, non-parametric tests, factor analysis, and cluster analysis. And these all depend sort of on what you want to compare with the data that you are looking at and what you are really trying to find out through that. Other functions of SPSS, other than just the storage and analysis, are that you can use it to edit data because raw data tends to be in need of cleaning before it can be fully analyzed. You can do this through running numeric functions, string functions, data functions, and more that will sort of clean the data and make it ready for analysis. And it can also be used to create tables and charts in which SPSS charts can sort of tend to be clumsy and ugly looking. However, they can still be used to create better looking charts if you apply templates because the analysis is still the same in the data that you are creating. Here are some of the references, and are there any questions?
Thank you for that excellent presentation. Are there any questions or does anyone have anything to add? I would like to comment on the presentation that Philip did to SPSS. I think SPSS has many different capabilities, and it's a good idea to know exactly how to work with the data. As Philip has said, data must be cleaned in order to work with it. So SPSS is very good for data analysis. Thank you, Philip. Okay, Dr. Lopez, do you have anything to add?
One more point. Yeah, I think if you gain a knowledge of SPSS, SPSS and Stata have similar coding. I think everyone, if you learn either of those languages, it's a little interchangeable. Some of the codes are different, but obviously it's not as a big jump as you've seen with R or maybe another MATLAB or one of the other analytical programs. So SPSS and Stata are similar where when you go into the software, you have to work within that program and then set the code up in there. I think what's kind of unique is the add-ons. I think Phil alluded to at the end, you can definitely work on a little bit more imagery with the add-ons with the SPSS updated version. There's capabilities of doing more, maybe varying charts and tables to present the data. And really, when you try to do that translational medicine, that translational science, translational analytics, it's to get people to understand the data that you've analyzed. So once you do that, you need to kind of put it, and that's why we always kind of mess around with the charts and tables. It's just so that the readership can understand the data a little bit easier.
All right, thank you for the presentation, Philip. Our second intern is William McIntyre, who is a senior from Howard University. William will be presenting on contingency tables. William, when you are ready, may you please share your screen?
Can everybody see my screen? Okay. Thank you, Nadir. Hi, everybody. My name is William McIntyre. I'm a rising senior at Howard University studying sports medicine. And today we're talking about contingency tables. So what is a contingency table? So what it is basically just like a table that summarizes data. What that means is a table that is a tool used in statistics to summarize the relationship between two categorical variables. It also displays frequencies or counts of observations that fall into each combination or category, so each variable basically. And most common format is a 2x2 table, but also larger tables such as 3x2 and 4x3, etc. And these are also used as well. And today I'm talking about the different forms of distribution that categorize the data. So the structure of the table. So it's a basic layout with rows for each variable. So like example would be gender, and then columns for another example to be like a favorite pet. And also, each cell contains a number representing how many people fall into both categories. So some people might fall into one category, whereas another person might fall into a different category. And the last row of the column usually shows the total amount of all the cells added up. And this helps to calculate the percentages of running statistical tests. And this setup makes it easier to see patterns like whether a group tends to prefer one thing over another. So this is the first example. The first example, it shows cell phone users who is and who is not a cell phone user. And if they are, it constitutes to why they got a speeding violation in that year or no speeding violation in the last year. As you can see in the X column, it shows speeding violations in the year and no speeding violations in the last year. Whereas in the Y column, Y row, it shows cell phone users and not a cell phone user. As you can see, the data from each row represents how many people fall in that category. So 25 people were cell phone users and 25 people violated the speeding last year. And whereas 280 people violated speeding violations last year, well, didn't violate speeding violations, and 280 people were cell phone users. And once you add those totals up, you get 305. And this is done for every table in every row. And then the last row shows the total of people that either violated the speeding violations or didn't violate the speeding violations. So what is relative frequency? So what it is basically is a table that shows a percentage or portion of the total observations that fall into each cell. So instead of just the raw counts. This helps to compare groups of different sizes fairly and better interpret relationships. So in this table, this shows the amount of times people like to study. So people like to study during the night or during the morning. So as you can see, more freshmen prefer to study in the morning than seniors, and more seniors prefer to study at night than freshmen. So as you can see, like I said before, each data is represented from each column in each row. So morning and night were split between variables, and freshmen and seniors were also variables. And the total amount of data is shown on the last column. So I use relative frequency. So what it does, it makes comparisons easier to do. So especially with unequal group sizes. It also is useful in survey analysis, marketing, and medical studies. It also highlights proportional relationships, not just raw totals. So this is a continue. So each row has its own frequency. So it's a total portion of each row's total. For example, in the freshman row, it's a total of 50 people in total, 50 freshmen. And what you do to find the relationship between frequency is you'll find the morning amount of people in the morning for freshmen, and then you divide that by the total number of freshmen in total. So as you can see, it's 20 freshmen here that prefer studying in the morning. So what you do is divide that by 40, the amount of freshmen total, and that will get you a 40% frequency for freshmen that prefer studying in the morning. You do the same thing for night for seniors. So you could do 30, which is the amount of freshmen that prefer to study, and amount of freshmen that prefer to study at night, divided by the total number, which is 50, and that will get you 60% frequency. So a conditional distribution. So a conditional distribution shows the proportion or frequency of one variable. This is given through a specific condition on one variable. So when they use conditional variables, this is used to make comparisons across groups very fairly. So it helps to really just reveal associations or trends. So for example, it could be, do seniors prefer to study at night, study more at night or more than freshmen? So as you can see, you can look at that variable, you can look at that condition and see it from the table that, okay, if I look at the seniors that prefer to study at night, it's obviously zero point 0.4, whereas the amount of freshmen that prefer to study at night is 0.3. So as you can see from the condition that more seniors prefer to study at night than freshmen. This is essential for probability, data analysis, and research. And then a marginal distribution. So a marginal distribution shows the total proportion or frequency for just one variable, regardless of the other variables. So think of it this way: a margin means it's the total number of margins, which is also known as edges, of a contingency table. So as you can see from the table, it's the same table before. So it shows the freshmen, seniors, and the total values. It also is differentiated by morning and night. And to find the marginal distribution for study time, morning versus night, you'll divide the total number of freshmen that prefer to study, well, total number of people that prefer to study in the morning by the total number of people that done the study. So it's 30 people in total. You'll get that from looking at the total distribution at the bottom. Then you divide that by the total number of people that have done the study. So 30 divided by 100 would be 30%. So 30% of people prefer to study in the morning. They do the same thing for people at night. So you see it's 30 freshmen here that prefer to study at night and 40 seniors that prefer to study at night. And what you do is divide that by 100%. So it'll be 75 by 100, that'll be 70%. So as you can see, 70% of people prefer studying at night. 70% of seniors prefer studying at night. And you're just using the column totals, which is the bottom row, and ignoring whether they're freshmen or seniors. So you're just using the X values to prefer or to see what each data value represents. Joint distribution. So joint distribution shows the proportion or percentage of the total number that falls into each specific combination or two variables. So basically what it means is the relative frequency for each cell in a contingency table. So to find the joint distribution of the study, you would do 20 plus 30, like I said, 20 plus 10, like I said before, and that'll get you 30. And you do is divide that by the total number of people, like I said before, and that'll get you the percentage of people who prefer to study in the morning. So just some takeaways. We explored four key distributions. So joint distribution, which is probability of two events happening together. Marginal distribution, which is the total number totals from one variable across all categories. And relative frequency, which is the proportions instead of raw counting, making comparisons easier. And conditional distribution, which is a percentage within a subgroup helpful for making focused comparisons. To conclude, contingency tables are powerful tools for organizing and analyzing relationships between categorical variables. These tools allow us to go beyond raw numbers to understand patterns, trends, and associations in data. This could be used for rugby research for us. We could use this to go into Excel and clean up data and to better analyze it and better understand it for people to use. And whether you're working in healthcare, sports, business, or education, or social sciences, mastering these concepts improves your ability to draw meaningful insights from data. These are references. And thank you. Are there any questions?
Thank you, William, for that excellent presentation. Are there any questions, or Dr. Lopez, do you have anything to add?
I think a good example is what we did with the under 20 analysis. If you look at those tables, we incorporated quite a few variables in our tables, even those that did not respond, which if you bring it up, someone brings up the paper, we can take a look at that really quickly, one of the tables. I think what happens is that because we're dealing with response data, it also takes into consideration another variable. That is those that did not respond to the study. So those that didn't answer the questions, but maybe they do have an injury, things of that nature. So it's very unique in that aspect when you kind of bring up does anyone have the paper up there? The under 19 paper?
Yeah, I could share my screen and show it.
So you could see that. And this way you can get an idea.
So there's a few tables that are in there. I think that this is like the first one. But like just an example is that you can see that like the totals add up in each of the columns for male and female right here. And then you see the distributions by location, type, and onset when we're talking about the distributions of location, type, and onset for specifically the medical attention injuries. Then down here, we have the time loss injuries, and we see something pretty similar.
And then all the players, as you see the numbers at the top, the N are the totals that respondents. And that's kind of unique in regard to making sure that you have the data fully, if you get what I mean. So therefore, you're actually just looking at the responses. Okay? No worries. Just want to make sure everyone saw that. We've already employed it, so make sure everyone tries to look at that when they look at their data.
Thank you, William. Our third intern is Mina Ko from Lydian Academy. Mina will be presenting on ANOVA. Mina, when you are ready, may you please share your screen?
Can everybody see my screen? Okay. So hi everyone. I'm going to talk about ANOVA, which stands for Analysis of Variance. And this statistical method is super useful when you compare 3 or more groups means and figure out if at least one of them is significantly different from the others. So what is ANOVA? It's basically a test that helps us to answer the one question is, are all these groups means the same or is at least one of them different? Unlike a t-test, which compares just 2 groups, ANOVA lets us handle 3, 4, or 5, however many we need without increasing the chance of making a false positive. So let's say you're comparing test scores from students who use 3 different study methods. Running a bunch of t-tests would increase the risk of getting a false result just by chance. ANOVA solves that by doing one overall test. It splits the variance into data into 2 parts. So one caused by the differences between the groups, and the other is by random variation within the groups. The bigger the between group variance compared to the within group noise, the more likely it is that something real is going on. So this is the math behind it. The key thing to remember is the F statistic. It's calculated by dividing the mean square between groups by the mean square within groups. So if that ratio is larger, it means that the groups are likely different, and then we will compare the F value to a critical value in the statistical table, or just get a p-value from the software. So, like most statistical tests, ANOVA makes a few assumptions. One of the assumptions is that your observation should be independent, and the data in each group should normally be distributed, and the variance across groups are about all the same. So that's called homogeneity of variances. We can check the third one by using something called Levene's test. And if these assumptions are way off, then we might need to adjust something or just use a different test altogether. There's 2 common types of ANOVA. So there's one way, which just looks at one factor, like different brands of running shoes or something like that. And two-way, which looks at 2 factors. So maybe it'll look at shoe brand and gender and even checks if there's interaction effect between them. So these are some visuals to help. On the top, you can see that there's its normal distribution for each group. The middle one is box plots that show how spread out the scores are. And then the kind of like the bottom one. Uh, this interaction plot helps us to see whether the combination of variables affects the outcome like differently. And these visuals are really helpful to understand the data. So a typical like one-way ANOVA process would be you first set your null hypothesis, which meaning all the groups are equal. And then you calculate the statistic using the sum of squares. After you get your p-value, if it's below your alpha level, like 0.05, then reject the null. But ANOVA would only be able to tell you that a difference exists, not where. So if it's significant, you need to run a post hoc test like Tukey's to find out whether like which specific group is actually different. So an example would using R. So you have to use the AOV function to run ANOVA and summary, which would give us the F value and the P value. And then if you get a smaller P value, like 0.059, that means there's a statistically significant difference between groups. So you would reject it. But there's also a lot more. Two-way ANOVA would help us to explore like more complex with 2 variables, like I mentioned earlier. Repeated measures of ANOVA is great when you're testing the same group multiple times, like tracking rehab process progress over the weeks. And then if your data doesn't meet like ANOVA assumptions, then you can use non-parametric alternatives, kind of like one of the examples was either Kruskal-Wallis tests or the Friedman test. So to wrap it up, you would use ANOVA when comparing 3 or more means and make sure the assumptions are reasonably met. And if you have a significant result, then you should follow it up with post hoc tests to figure out where the differences are, and always visualize your data because it makes it easier to handle all these complex like data. And then here's the references for my stuff, and then here's the references for the visuals. Thank you.
Thank you for your presentation, Mina. Are there any questions, or Dr. Lopez, do you have anything to add?
Yeah, Minna, did you comment on the normality of the data within the, like it's normally distributed between each? So there's a limitation with ANOVA, and that is it indicates there's a significant difference between at least the two groups, means, but it doesn't pinpoint which specific groups, and it relies on a lot of assumptions that the data is distributed appropriately, um, you know, that there's equal variances across the groups, homogeneity of the variance, uh, you know, therefore you can get inaccuracies. So make sure, luckily, we definitely clean over our data for normality and make sure that there's good distribution. The thing is, when you analyze large data sets, there may be that problem. Say you want to compare 1 year of the public health school system data to all the other years. Therefore, you have that, problem in distribution, and you don't want to use that. So an ANOVA analysis of variance may be a limitation, to use in that normal, in that aspect, because obviously you're not going to be able to change the larger data set of the 25 years of, public school health data. But if you take that 1 year of data, that's going to be much smaller than the 25 years. So the distribution is the problem. All right, everyone. Good job.
If there are no more questions, then that will conclude our call for today. We thank everyone who joined us for the Rugby Research and Injury Prevention Group Analytics Series. Thank you.